Yes. So we'll do electromagnetism here. So electromagnetism. So children, today electromagnetism, some topics I will tell. I will tell you what do you mean by magnetic field, what do you mean by lines of force, and what happens, what is a swimming rule, and what is no rule, and what is right hand thumb rule, what is Maxwell corkscrew rule, and around the straight conductor how magnetic field is present, around the circular conductor how magnetic field is present. All these topics are there. Okay, so first one children, magnetic field. Girls, what is meant by magnetic field? Magnetic field means, imagine if magnet is there here, if magnet is there here, around the space, here if you keep object it will attract, here if you keep attract, here it will keep, but if you keep here it won't attract, if you keep here it won't attract, if you keep here it will attract. What is magnetic field, girls? It is the space around magnet. It is the space around magnet in which its influence can be felt. In which its influence can be felt. What is the magnetic field? It is the space around the magnet in which its influence can be felt. Okay, and normally it is denoted by B, and its units are oersted. Or in higher classes you will study Tesla, or you will study Gauss. Okay, so many units are there. Oersted is the best example for 10th class, and the formula is F is equal to mb, where F is force, B is magnetic field, M is pole strength. M is pole strength. Strength of each pole of the magnet is units are ampere meter. And magnetic field, inside magnetic field, what will be present? Inside magnetic field, what will be present means you should say it consists of lines of force. Magnetic field consists of lines of force, like this. Magnetic field consists of lines of force, like this, like this, like this, like this. So magnetic field consists of lines of force. Okay, lines of force. What are the elements of magnetic field? Elements of the magnetic field are dip and declination. What are the elements of magnetic field? Dip and declination. Just remember dip and declination. Words, terminology, definitions are not there in 10th class, so leave it children. So this is about the magnetic field. What is magnetic field? Space around the magnet in which its influence can be felt, and is denoted by B. Units are oersted. F is equal to mb. Magnetic field consists of what anyone will ask means lines of force, and what are the elements of magnetic field means dip and declination. You should say. Okay, this is magnetic field. So F is equal to mb, F is equal to mb. This is the formula. Okay, as you go to higher classes, you will study so many other formulas also, but 10th class, just remember F is equal to m. This is magnetic field, girls. So I hope you copied this. Did you copy? Shall I rub this, girls? Shall I rub this? Yes or
So
no?
1 minute, sir. Yeah, sir.
Yeah, children. So next step, what is line of force? We'll study. What is line of force? Next we'll study. I told magnetic field consists of lines of force. Now then you should know what are lines of force. Girls, lines of force we can't see, but we can draw them, we can feel them, we can make do experiment also. Lines of force we can't see, but we can feel them, we can draw them also. How to draw, sir? You will ask. How means take a white sheet, put a magnet, okay, take a small compass, put in different positions wherever the arrowhead shows, wherever the arrowhead shows, wherever the arrowhead shows, wherever the arrowhead shows, put dots, join all the dots, you get lines of force. No sir, we want any other method. Means take cardboard, keep a strong magnet, okay, put some iron sprinkling, iron sprinkles, you keep chilling here, iron filings, we'll say iron filings, small iron filings. And what you do after keeping on the cardboard, just gently tap the cardboard. If you gently tap the cardboard, all the iron filings arrange themselves like this, children, in the form of lines of force. Neatly they will arrange. Okay, so you can do experiment, you can draw them, you can feel them, but you can't see them. What is a line of force? How we are drawing? Wherever arrowhead is showing, there you are drawing. No, arrowhead is north pole, tail is south pole. So line of force is defined as line along which, keep copying children, line along which freely suspended north pole, freely suspended north pole tends to move. Tends means tries to, tends to move. Line along which a freely suspended north pole tends to move is called line of force. Line along which a free, this line, how we are drawing children, wherever north pole is showing the direction we are drawing now. Wherever north pole compass we are keeping freely compass. Wherever the north pole is indicating, we are putting all the dots and we are joining. That's why line of force is defined as line along which freely suspended north pole tends to move. Tends means tries to move. Line along which a freely suspended north pole tends to move. Now, lines of force also have got some properties. What are the properties of lines of force? Remember, children, outside always they move from north to south. Outside always they move from north to south. And inside, if you see, inside they go from south to north. Inside the magnet, line of force goes from inside south to north they will go. And if you see, they are closed. See, it is closed. It is closed and curved lines. They are closed and curved lines. They are closed and curved lines. And they are crowded at poles. If you see at poles, so many lines of force will be crowded. Why they are crowded at poles? They are crowded at poles because poles are comparatively stronger than the middle of the magnet. Poles are comparatively stronger magnetic strength than the middle of the magnet. So these lines of force, so many you can see near the poles. Why? Because poles are stronger. Next one, fifth one. Okay, and no two lines of force. They will go from near also, but they will never intersect each other and go like this. No two lines of force will ever intersect. No two lines of force will ever intersect because if they intersect, if they intersect, field is in two directions. Field is in two directions, which is not possible. Which is not possible. Okay, children? Field is in two directions, which is not possible. If they intersect, field is in two directions. At a point, field will be either in this direction or this direction. At a given point, it cannot act in two directions. Field will be in one direction. So no two lines will intersect. If they intersect, the field is in two directions, which is not possible. At a given point, either right or left, but two directions it won't be there. And last one, if you, on the line of force, children, this is the line of force. No? On the line of force, any point you draw tangent. Any point you draw tangent. Tangent on line of force gives the direction of magnetic field at that point. Tangent on line of force. Tangent on line of force gives direction of magnetic field at that point. At that point. Only at that point. At this point, direction of magnetic field is like this. Tangent on line of force gives the direction of magnetic field at that point. So what are the properties, girls? Outside they are acting from north to south. Inside they are not acting from south to north. They are closed and curved lines. They are crowded at poles. No two lines will ever intersect. Why? If they intersect, field is in two directions, which is not possible. And tangent on the line of force gives the direction of magnetic field. Tangent on the line of force gives the direction of magnetic field. Tangent on the line of force gives the direction of magnetic field. So children, we have completed magnetic field, we have completed lines of force also. Properties are very important. Definition, properties. Definition, properties. Okay, children. Did you copy? Shall I rub this, girls? Girls, did you copy? Shall I rub?
Yeah, sir.
Next. Next. Remember. So, around the circuit, this is a circuit. If current is flowing, around a current carrying conductor, always magnetic field is present in concentric circles. Around a current carrying conductor, magnetic field is present. Around a current carrying conductor, magnetic field is present. Around a current carrying conductor, magnetic field is present. Who said that? Oersted. What is Oersted observation means? Around a current carrying conductor, magnetic field is present, he said. So how do you know that magnetic field is present? You have to keep one compass. If you keep any compass near to the current carrying conductor, it will show deflection. It will deflect like this, like this, like this, like this. It will deflect. Why compass needle is deflecting near current carrying conductor? Because magnetic field is present. A current carrying conductor produces magnetic field. A current carrying conductor produces magnetic field. How do you know that? If you keep a compass needle, it will show deflection. It keeps on deflecting. Why it will deflect? Because of presence of magnetic field. Current carrying conductor produces magnetic field. Who said that? Oersted. Current carrying conductor produces magnetic field. Who identified that? Oersted. How we will come to know? By the movement of compass needle. By the movement of compass needle. Now children, compass will move left or right. This is the question. Compass will move left or right. In which direction it will move? Yes, anyone? Compass will move right or left. To know the direction of deflection of compass, we will use swimming rule and snow rule. Two rules are there. Snow rule. Snow rule states that if current is flowing from south to north, then the compass needle deflects towards west. If current is flowing from south to north. So, children, imagine if current is flowing from south to north. Okay, imagine if current is flowing like this. Then we will take this south, this is north, this is west, this is east. If you keep a compass needle above or below, compass needle deflects towards west like this it will show. No sir, we need to understand this. Again, I will say, if current is going like this will take south, this will take north, this is west, this is east. If you keep compass needle above or below the wire, this will deflect towards west. Compass needle deflects towards west. No sir, we need to understand this. Again, I show. If current is flowing from south to north, west to east, if you keep compass needle, it will deflect towards west. Okay, if current is flowing from south to north, okay, then compass needle deflect towards west. Deflect towards west. No sir, this rule is confusing. Means one more rule I will say. That rule is called swimming rule. Swimming rule also gives the direction of deflection of compass. Swimming rule states that imagine you are swimming in the direction of current. Imagine you are swimming in the direction of current. Imagine you are swimming in the direction of current. Then compass needle deflects towards your left hand. Imagine you are only swimming, children. Imagine you okay. Imagine you are swimming. Imagine here you are swimming. Okay. So this is your hands. This is your legs. Okay. Then the compass needle kept above or below will deflect towards your left hand. Imagine you are swimming in the direction of current. Children, imagine you are swimming in the direction of current. Okay. Okay. Imagine you are swimming in the direction of current, and the compass needle deflects towards your left hand. Imagine you are swimming in the direction of current. Imagine you are swimming in the direction of current, and the compass needle deflects towards your left hand. Imagine you are swimming in the direction of current, and the compass needle deflects towards this is left hand, left hand. So any rule we can use to know the direction of deflection of compass kept near current carrying conductor. Compass needle will deflect. Which direction it will deflect? Towards your left hand. Compass needle will deflect towards your left hand. If you imagine yourself swimming in the direction of current, this both rule gives the direction of deflection of compass. This both rules gives the direction of deflection of compass kept near current carrying conductor. A current carrying conductor produces magnetic field. Who said that? Oersted. Next. Next. Around the current carrying conductor, magnetic field is present in the form of concentric circles. Around current carrying conductor, magnetic field is present in form of concentric circles. Girls, is it present in these concentric circles will move in clockwise or anti-clockwise? Which direction? These concentric circles will move in clockwise or anti-clockwise? Anyone? Can anyone say? It is not our wish, girls. It depends upon right hand thumb rule. It depends upon right hand thumb rule. What right hand thumb rule states that means imagine you are carrying conductor in right hand. Imagine carrying conductor in right hand. Okay, thumb in the direction of current. Then curling of the fingers gives direction of magnetic field. Imagine you are holding current carrying conductor in right hand. Thumb should be in the direction of current. If upward, put up. If down, put down. If left, you put like this. East, like this you put. Okay. Imagine current carrying conductor in right hand. Thumb in the direction of current. Then curling of the fingers gives direction. If current is going upward, my fingers are rotating like this. Right? This means anti-clockwise direction. If current is going down, my fingers are rotating in clockwise direction. So current is going, magnetic field is in clockwise direction. So if current carrying conductor is in right hand, current carrying conductor is in right hand, thumb in the direction of current, thumb in the direction of current, thumb in the direction of current, then curling of fingers gives direction of magnetic field. No, sir, this rule is a little bit confusing. It's one more rule is there. Maxwell corkscrew rule. Maxwell corkscrew rule. What does Maxwell corkscrew rule say is that if you imagine a screw, if you imagine a screw, okay, okay, tip if you take in the direction of current, tip, tip if you take in the direction of current, I'm sorry, then rotation of head gives the direction of magnetic field. If you take tip in the direction of current, then rotation of the screw head gives the direction of magnetic field. Girls, suppose you are fitting like this, like this, like this, like this, like this, like this, you are fitting. Means current is going in this direction, then magnetic field is acting in this direction. Like this, if you put on it, it will go inside. So, if you want to remove, if current is coming like this, then magnetic field is acting like this, like this. So, our rotation of the head of the screw gives direction of magnetic field. Tip of the screw is the direction of current. Tip of the screw is the direction of current. Rotation of the head of the screw gives direction of magnetic field. So this is right hand thumb rule. Maxwell corkscrew used to know the direction of magnetic field. Right hand thumb rule, Maxwell's rule used to know the direction of magnetic field. And swimming rule, snow rule gives the direction of deflection of compass. Right hand rule and Maxwell rule gives the direction of magnetic field. In which direction? Clockwise or anti-clockwise? And last, around the straight conductor, around the straight conductor, magnetic field is always circular in concentric circles. No, sir, I will take circular conductor means if you take circular conductor, then magnetic field will be straight. Then magnetic field will be straight. If you take straight conductor, magnetic field is circular. No, sir, I will take circular conductor means magnetic field will be straight. But in both the cases, magnetic field is directly proportional to current. You send more current, you'll get more magnetic field. You send more current, you'll get more stronger magnetic field. But in both the cases, it is inversely proportional to radius. Means here magnetic field will be very very high, but as you go away magnetic field decreases. As you go far magnetic field decreases. As you go far magnetic field decreases. So B is directly proportional to I and inversely proportional to R. This is called Biot-Savart's law. You will study in higher classes children. So around a straight conductor magnetic field is circular. Around a circular conductor magnetic field is straight. Okay, this diagram is also important. On what factors it will depend. The magnetic field depends upon current and distance. Directly proportional to current. More the current, more is the magnetic field. Inversely proportional to upon distance. As you go far, magnetic field decreases. But near, magnetic field is more. So children, we studied magnetic field, lines of force, swimming rule, snow rule, right hand thumb rule, Maxwell Cox rule, straight conductor, circular conductor. All these things we have studied. Anyone have any doubts in this? You can ask me.